In this lecture, I want to talk about how to find volume using a technique called the disk method, and that's going to involve integration. So first, let's talk about what we mean by volume, because ultimately, this is volume of a solid of revolution. And what we mean by that is that we're going to revolve some curve. So in this case, I'm giving a specific example: y equals square root of x. Looks something like this, and we would revolve it around the x-axis. That's one possibility. All right, we can revolve around the x-axis. Now it kind of has a lower piece as well, and it's solid. It's not hollow, right? So you can think of this almost looking, a little like a bullet. So it should be symmetric, but I can't draw very well, so just use your imagination. But the idea here is that we've revolved a curve around a given axis. It could be the x-axis, could be the y-axis, it could be another horizontal line or another vertical line. But you revolve it around, and you end up with the area carves out a solid piece, right? So this is really 3 dimensions, but we're just kind of looking at it in 2 dimensions right now. And so the question is, how can we find given that there's a certain amount of symmetry here because we revolved a curve around an axis, how could we find the volume of this solid? And as the name suggests, what we're going to do is we're going to take a little slice, a disk, out of this piece, right? So you can kind of think of it just cutting out a slice like that. And let's start off with what would be the area. If we just don't think about the thickness right now, just think about the area. Clearly, by revolving it, we're going to end up, that shape is going to be a circle. And we know that the area of the circle equals pi r squared, right? So for this particular circle, the question is, what's the radius? Well, I'll use another color to highlight this. This would be the radius, and again, this is symmetric, so even though this one looks a little bit shorter, it would be the same on this side. We're going to call this the radius, but it's going to be a function of x, where this is x right here. Because notice that the radius is, and if I drew another disk down here, this radius would actually be smaller than this one. So it's a function of x. If I use this, and we might even consider this, like I'll call this x sub I, because it's different than this might be, I don't know, maybe like x sub 2, right? We'd have an x sub 1, an x sub 2, and keep on going, and up here we'd have x sub n, right? So in other words, if we chose n disks, right? So here's the big idea. We have n disks, we find the volume of each of them, and we add them all up. And then that would give us the volume of the whole solid. So this radius, though, depends on what x value we choose because the curve is changing. It could be going the other direction, it could go up and down, but the point is the distance from the x-axis up to the curve is our radius. And because the curve is a function of x, our radius is a function of x. So I'm going to call this x sub I. This is the radius associated with that particular x value. So the area of one disk would be pi times r of x sub I, the radius, squared. Now, we have a certain thickness here too, right? That thickness we're going to call delta x. It's just the change from x sub I minus 1 up to x sub I. And we're going to assume that the thickness of all these disks is the same. So we'll call it delta x. So the way to find the volume of one disk is to take the area and multiply it by the thickness. That would give us the volume. So that's going to be pi r x sub I squared times delta x. And then if we want to find the volume of the whole thing, what we're going to do is we're going to add them all up. So we sum from I equals 1 up to n. And then finally, because basically we're going to miss a little bit, right? Because this is changing, so this is going to actually, this circle is going to leave off some. So what we want to do in order to fit our disks in better is have more of them, and ultimately we're going to let the number of disks go to infinity. So this would give us the exact volume of this. But this part right here, anytime we see a sum that goes a sum of n, and then we let the limit of the number of those things go to infinity, that's basically our integral. So we're going to replace that with an integral. And what are going to be our limits of integration? Well, let's assume this starting point here is a, and this ending point x sub n, we'll call that b. So we're going to integrate from a to b. And pi is, if you think of it, will be pi r of x sub 1 squared delta x plus pi r of x sub 2 squared delta x plus pi r of x 3 squared, and so on. Notice pi is a factor of all of those terms, so we can bring it out front. In other words, we can bring it outside the summation, which means we can bring it outside the integral. And then I've got r of x sub I squared, and as the number of these disks go to infinity, the thickness gets infinitely small, and we call that dx. It goes from delta x to dx. So this is our formula for volume. That's what we get out of this. So let's think about how we could, let me just give you a quick example using the specific one that we have right here. And we'll look at this if a was 0, so we went from 0 to 4 on the x-axis. What would be the volume of the solid of revolution using this particular function right here? Well, let's use our formula. The volume would be, we would have pi times, and this is going to go from 0 to 4. And what would r of x sub I be here? What would be our r of x? Well, it's going to be, we already said, it's going to be the distance from the x-axis up to the curve, which is, for any value of x, we could find the y value, or the height, this radius, by taking the square root. So that's going to be the square root of x. And then we're going to square it, dx. All right. So let's just go ahead and complete this then. So pi, and that's going to be, well, the square root of x squared. Well, I'll just rewrite this. Square root of x squared is just x, right? So this is a pretty straightforward antiderivative to find, right? It's going to be pi times, and it's going to be x squared over 2, and we're going to go from 0 to 4, right? So that's pi times 4 squared, which is 16 over 2, minus 0 squared, which is 0 over 2. So that's just 8 pi. Okay, so that's a pretty straightforward application of the volume formula. So let's look at a few more examples that aren't quite so straightforward that we have to think about. So here we're going to find the volume of the solid formed by revolving the area between 2 minus x squared and y equals 1 around y equals 1. Now I think it's helpful always to start with a picture. So let's draw a picture of this, what's going on here. Right? So let's see, we'll call this y equals 1 right here. That's the line y equals 1. And then 2 minus x squared. Well, when x equals 0, y equals 2. So our y-intercept is 2, and the negative x squared indicates that it's going downward. But we're just looking for this area right here between 2 minus x squared and y equals 1. And that's going to get revolved around the line y equals 1. So we're going to have the bottom half of this will be parabolic. It'll be symmetric about that line. All right. So we can think about just kind of carving out a disk again and thinking about, the volume of one of those, adding them up, using our formula. All right. Well, our formula is pi integral from a to b. And then we'll think, what we have to think about is what will be our bounds and what will be, well, let's just put the formula back up here for a moment. So here's our formula. Oh, sorry. The x sub I is only for the summation. Once we get to here, it's just r of x, right? In this case, the square root of x. All right, so what we have to think about is what would be our radius in terms of x, and then what would be the bounds, all right? That's what we have to figure out before we can fill this out. Well, these are the bounds. It'll go from here to here. So what we need to figure out is where does 2 minus x squared intersect with y equals 1? So let's just set them equal. 2 minus x squared equals 1. If I bring the x squared over and subtract the 1, I get x squared equals 1. and that's going to occur at x equals plus or minus 1. So here's negative 1, there's 1. That's our bounds of integration. And then we need to think about, and this is where I think it's helpful to draw this disk, is what would be that radius right there? How could we find that distance from here to here? And so it's basically going to be the top curve minus the bottom curve, right? So 2 minus x squared minus 1, right? You could think of it in this case as being similar, except that our lower one was y equals 0. So we didn't actually write it, but technically it would be square root of x minus 0. In this case, it's 2 minus x squared minus 1. Right? That would give us that height, which is the radius of that disk. And so if I simplify this, I'm going to end up with 1 minus x squared squared dx. All right. So this is most of the work goes into just setting the integral up. We have to find that r of x. We have to find the bounds of integration. The rest of it should be pretty straightforward. So if I square this out, I would get 1 minus 2x squared plus x to the 4th. All right, so now to find the antiderivative, I can just do that term by term. So the antiderivative 1 is x. Then I end up with 2 thirds x cubed plus x to the 5th over 5. That's the antiderivative. We're going to go from negative 1 to 1, and then take that whole thing and multiply it by pi. And if you plug that all in, I'm not going to do all the arithmetic here. That's kind of a waste of both of our times on the video lecture. I'm just going to plug it in and just tell you that that will turn out to be 16 pi over 15. All right. So again, here the idea what we had to do is find the limits of integration and figure out what our r of x is. Let's look at a different example. Okay, so here we're going to find the volume of the solid formed by revolving the region bounded by y equals square root of x, which we've already seen, with y equals x squared. So again, let's draw a picture. So square root of x, we know, looks something like this. And then y equals x squared looks something like this, right? So this is y equals x squared. This is y equals square root of x. And we know they're going to intersect, when x squared equals the square root of x. That's going to happen in two places, 0 and 1, right? So that's going to be, because we know that 1 squared is the same as square root of 1. So that's going to be our bounds. And then we're going to take this region here, and we're going to revolve it around. See how if I can do this one a little bit better than the first one, something like this. And then we're going to, we have the same type of a thing down here, so something like this and like this, right? So it's just this piece. So basically, this middle part is not there, right? I mean, that's just my disk here. So one way to think of this is that you have an outer part, which is basically, if I go back to my original example, the outer part is this whole piece, and this inner part is being removed, right? This part between y equals x squared and the x-axis is kind of being bored out of the middle, and so what we're trying to find is the volume of what's left, right? So that's, again, we come back to what would be our so let's first do the outer. We have actually already done the outer, right? So we have the outer volume, which is pi, and we're going to integrate from 0 to 1, and that's going to be the square root of x squared, right? That's the one that we've already done. And then the inner volume. So one way to think about the inner volume is it's the volume between x squared, and so if we just took x squared and we evolved around, like we have a smaller disk here. Let's think about it like this, right? This is just going to be y equals x squared, right? That's what that radius is going to be. So if we take this this inner volume and subtract it off, then from the outer one, then that would give us the volume that we're looking for. So that inner volume is going to be pi 0 to 1, and it's going to be x squared squared dx. All right. So the volume we want is going to be the outer minus the inner. All right. Well, I'm not going to do this one again. We've already done that one. We know that's going to be 8 pi. And so let's do minus, and now we're going to integrate pi 0 to 1. That's x to the 4th dx. Right. So that's 8 pi minus pi times, that's going to be x to the 5th over 5, 0 to 1. All right. So when it's all said and done, we're done with the arithmetic, we're going to find that that's 3 pi over 10. So this is one way I think, to me, this makes the most sense. You just think of this scenario where we're looking at the area between two curves and we're revolving that around an axis. Is you just think of, well, what's the outer volume? What's the volume if I didn't have this inner piece? If I just had square root of x, I could find that volume and then find the volume of the inner one and subtract that off. This is also called the washer method, because you can kind of think of this whole thing being, we have this bigger disk here. So let me think of it like this. So notice this looks like a washer because we have this bigger disk and this inner disk that's being removed, and it leaves us with a washer. So the washer method, you're going to go from pi square root, or sorry, not square root, the integral from a to b, and you're going to have the outer, so this is the outer radius minus the inner radius. All right, so because basically what we did is we took this and we subtracted this, but we can boil that down to one integral where you have square root of x squared minus x squared squared. We could do them separately, which is my preference, but I wanted to kind of point out there's another way to think about this and to just write it as a single integral. And again, this washer method is relevant when we're looking at a scenario where we're finding the area between two curves, and that's what's being revolved around the x-axis. All right, last example I want us to look at is one where we're revolving something around the y-axis. All right, so let's take a look at what this would look like. So we're looking at y equals x squared, and y equals x squared looks like this. And we are going to revolve this around the y-axis. So we're going to end up with something like this. And we're looking at this on the x-axis from 0 to 2. So this x value right here is 2. Well, in this case, what happens where this gets different is now when we're putting in, well, again, maybe just use a different color. If we take out a disk here, that now our disks are horizontal instead of vertical. And so what we want to think about is now our radius is going to be in terms of y instead of in terms of x. So if we just take this and say, well, if I go from 0, that's, x equals 0 out to x equals what, right? So let's solve for x here. X equals the square root of y. All right. So on the y-axis, let's think about this then, right? How far are we going to go? We're going to start down here at y equals 0, and where are we at here? When x equals 2, y equals 4. All right. And then we want to think about this distance. This is going to be the square root of y minus 0. So there's my radius in terms of y. All right. So we just have to kind of convert everything back to y in order to, if we're revolving around the y-axis. And that's not always possible. We can't always solve for x in terms of y, so these will be kind of a special case. We'll see another method. There's another method for this in cases where we can't solve for x in terms of y like we did here. So to set up our integral then, we have pi, and we said on the y-axis we're going from 0 to 4, and then r of y is square root of y squared. Alright, well this turns out to be pretty much exactly the, notice this is exactly what we did here. We went from 0 to 4. So this is the exact same figure, except now it's on the, it's revolved around the y-axis instead of the x-axis. So in the end, it'll be exactly the same.